أعوذ بالله السميع العليم من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله وبركاته and hello everyone. So we come back again with another lecture of nuclear pharmacy with the code PHMC 2172 and PPPC 2721, and this time we're going into another topic entitled internal radiation dosimetry. So before we are going into further details on this particular topic, I would like to ask all of you to get yourself ready, open your heart, open your mind, because I'm going to bring all of you back into the world of mathematics, because there are a lot of calculation, a lot of equation that will introduce yourself for this particular topic. I think it already been mentioned by Dr. Zatusna as part of nuclear pharmacy working in the hospital. You need to prepare dosage to be administered to the patient, and before you prepare the dosage, you need to understand how much of radioactivity to be prepared for the patient, especially when we talk about the diagnostic purpose or the therapeutic purpose, and for you to understand on that interaction of the radiation and how much radioactivity can be delivered to the organ and so on. This particular topic will let you dive in further to understand on it. So get yourself your calculator, get yourself a calculator as well, because this will be needed for you to do a lot of exercising. I think I'm going to provide a tutorial question as well together with this topic, so for you to understand, because on this particular lecture we will much focusing on theoretical part only. So let's start now. So for today's lecture, we're going to divide into two big parts. The first one about radiation units, what are the units we'll use for this particular radiation dosimetry, and another one about the radiation dosimetry itself, the calculation involved, how you calculate, what kind of equation will be used to understand further on this particular topic. Okay, in radiation dosimetry, especially when we talk about international radiation dosimetry, we will use a specific radiation unit to understand the activity involved. So please don't get yourself confused with the radioactivity that we learned previously. So this particular radiation unit that we use is specific to understand the internal radiation dosimetry, especially when we talk about the dosage being given or being administered to the patient. If we look into details of radiation units, we can divide it into three basic units. So the first one is raw engine, second one is RAD or rad, and the third one is REM. So raw engine is actually we talk about exposure, while rad we talk about absorbed dose, and RAM we talk about dose equivalent. So if you all like to talk about the details, not just detail, I mean the definition of raw engine. So how exactly we talk about exposure? So we are talking about X-ray or even gamma radiation, which produce ionization of one electrostatic unit of either we talk about positive charge or even negative charge per cubic centimeter of air in terms of temperature at 0 degrees Celsius, and in terms of the pressure is 760 millimeter mercury, or equal to STP. So that's the definition of raw engine. You can look into details. What does it mean by that? I put it there on the notes. But when we talk about equation, so one raw engine is equal 2.58 times 10 over minus 4 coulomb per kilogram. So that's the unit. So that's we talk about raw engine. So where we can use raw engine, so it only applies to the air and to X or gamma radiation. So we're not talking about alpha or beta, specific to X radiation or gamma radiation, and it can be only applied if the photons is less than 3 mega electron volt energy. So if you are talking about something bigger, so we cannot use raw engine in terms of this particular case. Okay, how about rad? So as I mentioned earlier, so rad we are talking about the absorbed dose. So basically rad we use when we want to measure the energy deposited in unit mass of any material used by any type of radiation. So if you look into raw engine, it's specific to X-ray or gamma radiation, but for rad it can be used throughout X-ray, gamma, alpha, or even beta. So the SI units to be used for rad is gray or GY. So how exactly we got the gray? Basically, if you look back into one rad, so one rad equals to 100 ergs per gram absorber, and one rad also can equal 10 over minus 2 joule per kilogram. And we look into 1 joule, so 1 joule is equal 107 ergs. So when we do kind of conversion here, so we could get that 1 gray can be equal to 100 rad, and if you convert the unit is equal 1 joule per kilogram absorber. So remember that, put in your mind, red, the SI unit being used is gray. The symbol is GY. As I mentioned earlier, red is not restricted to any type of radiation, regardless alpha, beta, gamma, or even X-ray. It means that red, when we talk about a radiation dose of 1 rad or 0.01 gray, will always be 1 rad, regardless the material is 1 gram, 2 gram, or even 10 gram. Because when we talk about radiation, we are not talking about the weight. We're talking about radiation dose. So 1 rad will not change even the material is heavier or lighter. If started as 1 rad, it will be 1 rad internally. And we are talking about the integral absorb dose. So we can giving the unit into gram rads or G dot rad or gram gray. So it can be both. If you want, you can define it as gram rads or gram gray. Okay, I give you an example here. So if you're talking about a radiation dose to a mass of 45 gram material is 10 rad. Okay, so you have 45 gram material with a radiation 10 rad, or we're talking in gray 0.1 gray. And the integral radiation dose to the material is 450 gram rad or 4.5 gray, but the radiation dose will still be 10 rad. Okay, so don't get confused between the radiation dose and integral absorb dose. Radiation dose will be fixed, but the integral absorb dose will be manipulated or be affected by the mass. So when you have heavier mass, meaning you have higher integral absorb dose, but it will not affect the radiation dose itself. So it will keep, say here for example here, if it's 10 rad, it will keep it as 10 rad. Even like if you increase the radiation dose to a mass of 100 gram, because the radiation dose is 10 rad, it will keep it 10 rad. But if you have 440 gram, 450 gram, so just the integral radiation dose will be 4,500 gram rad. So that's the difference. So get yourself separately. Radiation dose fixed, integral radiation dose is subject to the mass times the radiation dose. Okay, now let's talk about RAM. So RAM we can divide into two different situations. So based on one situation, the definition of RAM or how we calculate RAM is different. So on the first situation, we are talking about radiobiology. So in situation of radiobiology, RAM or in the symbol HR, you define them as rad times RBER. So RBER is actually a relative biological effectiveness of the radiation. So that's in first case, we are talking about in radiobiology. But if you're talking about radiation protection, so we're talking about protection. So the way you define RAM, HR, is equal RAD or rad times WR. So WR is actually the radiation weighting factor for a given type of radiation. So in this case, the SI units, if you're talking about radiation protection, is sievert or SV. And if you look into this tag, 1 sievert or 1 SV is equal to 100 RAM. The weighing factor is already been fixed and it depends on the type of radiation. For example, here, the X-ray itself, the radiation weighting factor is 1, same with gamma rays, and same with electrons and positrons. And if we're talking about neutrons, the radiation weighting factor is continuous. And for protons more than 2 mega electron volt, the radiation weighting factor is 2. And for alpha particles, fission fragments, or heavy ions, the radiation weighting factor is 20. So usually when we talk about factor, it's already fixed value. So here how the RAM can be calculated. So it's subject to the rad. So the higher rad it is, the higher the RAM will be. So that's the basic of the radiation unit. So it just left a bit warm up for you to understand further, because the main important part is this one, the radiation dosimetry, where you will apply all the units involved and you will understand further into how we calculate the absorb and how is the relation between the source organ, target organs, and so forth. So before we go into further of the calculation part, which I think all of you might feel excited, I'm not sure whether you're excited or not, but I assume you guys will be excited. Let's look back into the situation about preparation of the radiopharmaceutical to be administered into the patient. So when we are giving this particular radiopharmaceutical, there are a few things that we need to take care of, especially when we're talking about damaging effects related to absorption of energy in tissues and organs. So what are the factors that can cause damaging effects when giving radiopharmaceuticals to the patient? Firstly is the activity of the administered radiopharmaceutical. So sometimes you have too low of radioactivity, causing an issue when you want to quantify amount of radiopharmaceutical that would be administered to the patient, or perhaps it's too high. And if it's too high, it might cause a complication also to the patient. So that's we're talking about the activity. And the second factor that can cause the damaging effects is about the physical and biological half-life of the radiopharmaceutical. So physical, we're talking about the radioactivity of that particular radionuclide tag with your pharmaceutical product. Another one is biological half-life, when it goes into our body, how long it can sustain in our blood circulation and so on. So if you have a very low physical half-life and also low biological half-life of the activity, it will cause trouble, especially like you to have enough time, or like enough window of frame of time to really allow the radiopharmaceutical to interact with the targeted tissues or organ. So that also can cause another damaging effect. And the third one, we are talking about the distribution and the metabolic fate of the radiopharmaceutical internally. So we are not just talking about the radionuclide that tag with the radiopharmaceutical. We are talking that particular pharmaceutical involved. How about the distribution? Will it be distributed equally or longer? How about the metabolic fat? Will be easily excreted from the body or not? So this will be a main factor as well, because like if you have very high metabolic fat and very short biodistribution in the body, you will not allow enough exposure for the radiopharmaceutical to reach the targeted area, and another one perhaps not even given enough time to allow, if we're talking about diagnostic, to image them, or if we're talking about therapeutic, not enough to cause the drug or the radiopharmaceutical involved to treat that particular area. And the fourth factor that we can really take care of is we are talking about the fraction of energy released per disintegration from a source region. So here it is like we want that, for example, like you want to treat particular targeted area, and then sometimes you cannot reach directly to that particular source, and also, or perhaps you need to inject a nearby, or even you inject that particular drugs into the targeted source. We need to look whether the energy release per disintegration is high or low. So it depends on the situation. For example, like you are going to treat the area we are talking, for example, liver, and then if when the radiopharmaceutical reach to the liver, and then it will, because we are talking about radiation, so we're not just like in the liver area, so you got kind of like released to the surrounding tissues or organ as well. So if you release more of energy to surrounding tissues or organ, instead of you are treating or diagnosing a particular area, you got a false result if you're talking about imaging, or perhaps you might cause other we're not talking about fatality, but cause kind of a damage to the surrounding tissues or area beside the source region. So this also needs to be calculated carefully. And last but not least, of course, we are talking about the target organs, the shape, the composition, and the location of the source as well. So this is really important. Sometimes the location is hard to reach the target, or sometimes the shape is too small, and the composition sometimes is not convenient for the radiopharmaceutical to be or to reach that particular area. Okay, if you look into this particular figure on the left side here, so we have target organ, we have the source organ. So if you look into this, so usually the absorbed dose is delivered to a target organ from one or more source organ containing radioactivity. And you need to actually calculate how much of the absorbed fraction dosimetry here. So how much of dose can be absorbed by target organ. So they got a case that you might can immediately reach to the target organ. Sometimes you need to deliver to the source organ. So for it to do the work, so you need to have enough radiation energy to reach the target organ. So if you have a low energy that been transferred or absorbed to the target organ, then you will not meet your objective to do with a treatment or therapy. So usually this we're talking about the treatment part. If talking about diagnostic, you want to be localized at particular targeted tissues or organ. And sometimes the source and target organ might be the same. So in this case, the figure is different, but then if you're talking about diagnostic, usually the target and source are usually similar one. But if we're talking about therapeutic, it can be different from different source organ. It can be also the target is also the source organ. And of course, why you need to understand on this one, because another factor that you need to understand, we want to know that we don't overdose our patient just because you want to ensure that the target organ receive enough radiation energy for the source organ. Because if you have too high concentration of radioactivity that exceeds average concentration in the body, it can cause fatality to the patient. So this needs to be careful. So next I will explain the steps or the procedure how you want to calculate the radiation dose to a target organ from a source organ. So first step, what you need to do is to determine the amount of activity and time spent by particular radioactivity in the source organ. So why you need to understand this? Because if you have greater activity and longer time, meaning that it will be a greater or higher radiation dose will be given. So you need to understand on this part. So after you determine the amount of this particular activity and time span, then you can go with the next step where you calculate the total amount of radiation energy emitted by the radioactivity of the source organ. So once you got the amount of activity, we got the time, then you can calculate on the emitted radiation energy. So this radiation energy is depends on the energy and also the frequency of emission of the radionuclide. So you need to know this, because like if you have a lower frequency of emission, meaning that the total amount of radiation energy might be affected as well. So that's the second step. And the third step is like you need to determine the fraction of energy emitted by the source organ, which it will be quite equal to the energy that we absorb by the target organ. But again, this kind of fraction of energy is subjected to the type and energy of the emission. And of course, we are talking about the anatomic relationship between the source and target organ. Here we're talking about the size, we're talking about the shape, and also the distance between the target and the source organ. Because like the more distant you will be, meaning that the energy that will be absorbed by the particular source organ for the target organ it might be lower, because like, it took time for the energy to reach or and absorbed by that particular target organ. Okay, I almost forgot. So the method that we use to measure the radiation dosimetry, we call it as MERT method. So you can Google to know further about it, but this is the method. So in order to understand this particular method, there are a few equations that you need to know, and afterwards we'll try to do some kind of tutorial to actually use this info to understand further. So the first one that I'm going to explain, we are talking about cumulative activity. The symbol is A with a tilt on top of it. So what exactly is cumulative activity? So cumulative activity, we are talking about the amount of activity or radioactivity present in the source organ, and also on the length of time which the radioactivity is present. So if we're talking about the SI unit, so the SI unit for cumulative activity is becquerel second, and the symbol is BQ.SEC. So the B must be on capital. And we also have the traditional unit. So traditional unit that we use is microcurie hour. So I think you heard the curie before when we were talking about the radiation at the earlier part. I think explained by Dr. Kamal, if I'm not mistaken. So 1 microcurie is equal 3.7 times 10 over 4 becquerel. And then 1 hour, we have 3,600 seconds, right? So if you are looking into 1 microcurie times hour, it equals to 3.7 times over 4 times 3600, and then we convert everything, you got 1.332 times 10 over 2 megabecquerel second. So that's actually the SI unit for cumulative activity in 1 mercury in an hour. So if you have a graph like this where the x-axis is the time in seconds and the activity in becquerel, so the area or below of the graph is actually the cumulative activity. So how you can measure it? So if you look back into mathematics, whether you learned it when you were SPM or you learned it when you were foundation, I'm not sure whether you learned this in the foundation, but because my background was engineering, so this kind of mathematics is always there each year of my degree level. So you just do some kind of integral. So you have from 0 to infinity, and then you just measure the cumulative activity. So here, like if you want to measure from 5 seconds to 20 seconds, just put 0 to 20 seconds, and then you can measure the cumulative activity by the area below the graph. Okay, in order to use this into detail of the cumulative activity, because we are talking about interaction between one particular tissue organ to another particular tissue and organ, and it also involve the biological half-life and so on. So we divide it into 3 different situations. So in situation 1, if the uptake of your radionuclide or radiopharmaceutical by the organ is instantaneous, meaning that the radiopharmaceutical was uptake very rapid with respect to the half-life of the radionuclide. There's no such thing, we are not talking about biological half-life, and there is no such thing as biological excretion, meaning that your radiopharmaceutical is not excreted through feces or even to urine. So you can use the equation like this, the chemical activity equal to 1.44 Tp times A0. So Tp is the physical half-life and A0 is the starting of the radiation activity. Okay, how about in a situation where there is no physical half-life, but this time there is biological excretion? So in this case, the uptake is still instantaneous, but you have clearance by biological excretion only, and there is no such thing as physical decay. So the equation that we'll use to calculate or determine the cumulative activity is 1.44 Tb1F1A0 time plus 1.44 Tb2F2A0 etc, etc, etc. So here that the TB1, so B is biological half-life, so the first half-life, and then you have starting point, the second one, and so on, and so on, and so on. Okay, the third situation where right now you have both situation where you have physical decay and also biological or biological excretion. So in this case, the uptake is still instantaneous, and you measure or calculate the cumulative activity by 1.44 Te times A0. So T is a calculation between the biological half-life and physical half-life. I think you got the equation previously. You learned that before how to measure Te. So I need you to look back into the previous lecture notes to determine how you got Te first. Okay, that's about the cumulative activity, or A with a tilt as the symbol. Now I would like to talk about the equilibrium absorbed dose constant. So the symbol is delta. Okay, this kind of triangle we call it as delta. So given the cumulative activity for the source organ, now we need to calculate the radiation energy emitted by this amount of cumulative activity. So as I said, the equilibrium of this absorbed dose constant or delta you can calculate into this equation, which delta T equal 1.6 times 10 over minus 13 NIEI. So the unit is gray kilogram over becquerel second. So what is EI? EI is actually average energy in mega electron volt of the ith emission. And what the NI? NI is actually relative frequency of that emission by the radionuclide. So this is the equation, but if you want to convert the unit into rad gram per mercury hour, so it will become something like this. So delta I equals 2.13 and IEI. Okay, so this is SI, so this is a traditional unit. So it depends, and do check the question. Sometimes question might trick you, want to ask in radiation or might ask in grade. The next part that I would like to explain to all of you will be the absorbed fraction. So the symbol is phi. Okay, this is the symbol phi. So the absorbed fraction actually depends on how much of energy or radiant energy reached to the target organ. And another factor that will affect the absorbed fraction is how much of the volume and composition of the target organ. So the amount of radiation energy and volume composition will affect how much of absorbed fractions will happen. And the notation that we use for absorbed fraction is phi I. In the bracket, we have RK and RH. So the arrow is from RH to RK. So RH is referred to the source organ and RK is referred to the target organ for the ith emission. Okay, let's go into the details of the equation. So if you're talking about the total energy absorbed, so the SI unit is gray kilogram. So this is how you use the symbol. So the accumulated activity times the total energy absorbed of this. So you have this epsilon and then the total of it n times the delta T. So delta is equilibrium absorbed dose. So this is the total energy absorbed, and then if you are going to measure the energy absorbed by target organ, which divided by target organ mass, you will have something what we call it as the average absorbed dose increase to the target organ, and then the equation will be something like this. You have D bar and RK from RH to arrow from RH to RK, and there will be that accumulated activity, so mean the total energy absorbed divided into the target organ mass. It will give you this value, which average absorbed dose increase. Okay, if you want to measure a specific absorbed fraction, so what you need to do, you just have the absorbed fraction divide into the total mass of the target organs, something like this. And that it means that if you can have a average specific absorbed dose by have the total accumulated activity times the total specific absorbed fraction times the equilibrium total, the delta here. So it gives you the average absorbed specific absorbed dose. And a theorem also said, what we call it the dose reciprocity theorem. It mentions that in an organ pair, regardless which one is source, which one is talent, if you inverse any of this or reverse any of this, the total or the specific absorbed fraction will be the same. Whether A become the source and B become the target, and then you change B become the source, A become the target, is still similar. Another point that I want to add here when we're talking about internal radiation dosimetry is about calculating the mean dose per cumulative activity, or denoted as S. So why there is need to calculate this particular point? Because when we are talking about radiation dose calculation, especially when we're talking about penetrating radiation, it can be a little bit complicated, sometimes very tedious. Especially when you are facing multiple emissions when you're doing the internal radiation dosimetry. So that's why people determine by using this as it make easy for you to simplify the whole problem you are facing here. So how exactly you measure S? So usually you have S, and in bracket you have targeted organ and then the source organ here. So if you simplify the equation, it can be like the total specific absorbed dose times this delta T. So in other way, if you kind of like change the equation, you can determine something like this. The average specific dose equal to cumulative activity times the mean dose per cumulative activity. So you have this one, and you times the cumulative activity, you can have the mean dose absorbed dose here. So however it is, you can determine all of this as long as you have the information of the starting radiation activity. So usually the S value will be given immediately when you want to measure the average dose here. So for example, if you look into this table, we have a table of the S value for technetium 99M in adult male phantom. So how you measure this? So you need to know what is the target organs and what the source organ. So you look at, for example, you have brain as the target organ. If your source is the liver, so the amount or the value of S is something like this. So you can refer this table as in your textbook, which is much clearer. So I just screenshot this just to show you here. And for information, the S value is not just subject to the target organs and the source organ, it's also subject of the type of radionuclide that will be used. For the one that I showed you previously is the technetium-99M. So this one is 1p1 iodine. So each S value will be different based on what type of radionuclide you are using to tag with your pharmaceutical product. So that's it for today's lecture. So I think all of this I mentioned earlier is about theoretical only. I will provide a tutorial questions for you to understand further how to apply these uh, equations and how to use it, because as usual, this is really important for you to not just memorize the equation. Is much more important is how you want to use that equation to solve the problem or issues related with internal radiation dosimetry. So that's it from me. So I will see you in the next lecture, which will be your final lecture for this course. I will upload the videos as soon as possible. And again, sorry for the delay of this particular video. And if you have any questions, don't wait for me to ask you. Feel free to email me or contact me through the Telegram group, and you may ask me any question related with this particular topic. So thank you. That's it from me. I wish you all the best, and please stay safe in this CMCO. Assalamualaikum warahmatullah, and have a good day.